Welcome back to this course Advanced Manufacturing and Process Modeling. So, today we will discuss about the different numerical methods that we generally consider to solve the manufacturing processes related problems. Again, to gain insight into the process physics and also to optimize the conditions so that we can get the desired quality characteristic in the concerned manufacturing process. So this slide you can see that there are now couple of processes has been simulated over here. So you can see under from here you can see the billet which is getting solidified, and you can see this is a problem where the heat transfer and also the melt pool formation in case of fusion welding has been simulated by finite element modeling technique. And so this is a classic example of solidification transport phenomena by finite volume method. And again this is another example of solidification transport phenomena during single pass additive manufacturing using laser powder bed fusion route. And so this one is the example of rolling simulation where the finite element method is employed to simulate the rolling process using a 2-high roller. However, here only one roller is modeled for simplification and to reduce the computational cost. And so you can see how the rolling is getting done over here. So, and here you can see the how the single pass build is getting deposited with the onset of laser movement over the track, over the substrate. And so in this slide you can see a typical example of orthogonal machining where you can see the chip formation. So this is a example of finite element modeling technique that is applied to simulate machining process. And here you can see the example of wire drawing. Again employed finite element method has been employed to develop the model, and this is the example of the micro scale model of 2-sphere 2-particle sintering at the in case of solid state sintering process. So this is basically showing the effect of diffusion and diffusion based molecular bonding between the neighboring powder particles. And here you can see so in this image you can see that the macro model of sintering of alumina nanopowders, and this image shows the linkage established between this macro model and the micro model of sintering in case of alumina nanopowder. So you can understand from here the importance of the process modeling in manufacturing problems, where we can basically identify the actual. So for example, in case of sintering we can identify the sintering temperature and the heating rate, and also the cooling rate the specimen need to be subjected post sintering is done, and what should be the isothermal holding period during sintering. So all those parameters, process conditions we can identify by doing accurate numerical, developing accurate numerical models, and that can save a lot of time which is otherwise needed if you need to optimize those using experimentation alone. And also it is it saves time, it is cost effective, and also parallelly it gives insight into the physics. So here from you can understand how the process physics, how the diffusion is happening, how the bonds are getting established, and how the densification mechanism actually takes place. So all those details you can understand by developing numerical models. So these are the twofold objectives of developing numerical models of the manufacturing processes. So so what are the steps in numerical method? So the steps are developing a mathematical model and interpreting the governing equations, and then dividing the domain into a set of discrete nodes or elements or set of control volumes in individual techniques, like like we divide the domain in the form of elements in case of finite element method, and we divide the domain by a set of control volumes in case of finite volume method. but what is intrinsic to all these numerical methods is that we are basically trying to convert the partial differential equations, I mean the governing equations, into a set of algebraic equations, so that their solution becomes much easier than analytic solutions. And how we do that? We solve the system by converting the PDEs in the form of linear algebraic equations, so that we can achieve the solution at nodal level, and then that I mean we can estimate the distribution of the of the particular physical parameter, I mean like for example temperature or viscosity or maybe the fluid velocity. So, all those parameters we can identify. Same is true for solid state deformation, like stress and strain distribution in a solid sample which is undergoing deformation. We can estimate those at all the nodes present in the domain, in the discretized domain. So, here you can see this is the flow chart which shows what we do in basically the process modeling of the manufacturing processes. So, so basically it solves the so basically it is a combination of physical domain and physical phenomena that we are trying to resolve by developing numerical models. So, the concerned set of governing equations which are applicable in that given computational domain, we identify those and then we discretize the domain, we generate the grid, and then we arrive at the set of algebraic equations which are the simplifications or which gives approximate solutions to the PDEs, which are and then we concerned solution technique we implement, and then we find the numerical approximate solution, which is often quite close to the the solution we can get by analytical techniques, although it can become much costlier and time intensive to solve the governing equations analytically, and sometimes it poses significant challenges which is otherwise much easier and cost effective to solve them by numerical methods. And then of course, the numerical solutions are subjected to experimental validation, because without validation we cannot justify the implementation of that particular numerical method to solve the problem in hand. So with this we will start with the finite difference method, which is one of the basic method of to achieve numerical solution of PDEs, and it is believed to have been introduced by Euler in the 18th century, and so this method is known for its simplicity. So, finite difference method starts with the conservation equations in their differential form, and then we basically generates a grid, and so that we can solve the partial differential equations, and then we convert them in the set of algebraic equations. So, and there are a couple of different techniques of finite difference method which are like forward difference, backward difference, and central difference. So, these are different schemes. So, depending upon the accuracy on demand to solve that particular problem, it can be a flow problem, it can be a deformation problem, it can be a heat transfer problem, so on and so forth. So, based on the accuracy on demand, we choose the appropriate finite difference scheme to solve the problem, and often finite difference is basically applied in case of structured grids, although it can be applied to unstructured grids, but it becomes much simpler and easier to apply those in case of structured grids. So, so here we will just see one example. So, this is a typical example diffusion equation which is shown over here. So, you can see, so here tau is giving you basically the diffusion coefficient, and phi is any property, and q is the source term. So, you can see how we can we can find the value of phi x by Taylor series expansion. So, so phi is equal to phi x is equal to phi x I plus x minus x I del phi del x I, and then x minus x I square by 2 factorial, so on. So, this is the Taylor series expansion, where you can see the value of h represents the remainder terms or higher order terms in the Taylor series. So, which we often neglect to save the computational time, and using these expansions one can obtain approximate approximations for the first and higher derivatives at point x I in terms of the functional values at neighboring points. So, here you can see a typical structured grid of where we can apply and we can solve using finite difference techniques. So, you can see this is so this is basically the particular node of interest location which is named as P over here. So, here you can see it is in Cartesian coordinate system. So, in the x side it is the increment in terms of I plus 1, and in the negative x side it is by I minus 1, and similarly in the y direction the increment is in the form of j plus 1 in the positive y, and in the negative y it is given by j minus 1. So, so difference the distance between two grid points in the x direction is delta x and in the y direction is delta y. So, here you can see from this equation. So, again if you are trying to identify the value of the primary variable u at the location I plus 1 j, that is which is situated towards the right from the identified node P. So, here if you again apply the Taylor series expansion, so you can get, so u I plus 1 j is equal to u I j plus del u del x I j delta x into plus del square u del x square I j into del x square by 2 and so on. So, so this is the above equation, and pursue our discussion of finite difference representations of derivatives. So, from here we can identify the achieve the value of the derivative, that is the first derivative of u in terms of x. So, del u del x at I j we can identify the value by because we have already estimated the value of the primary variable at u I plus 1 j. So, del u del x I j can be expressed in terms of u I plus 1 j minus u I j, value of the primary variable at the point nodal point P, by divided by delta x, that is the distance between the point I plus 1 j and the point I j. So, minus these are the higher order derivatives. So, which are minus del square u del x square del x by 2 plus del cube u by del x cube. So here from we can get that u I plus 1 j minus u I j by delta x is a finite difference representation of the partial derivative, that is del u del x. So, the remaining terms on the right side constitute the truncation error, which we can neglect. So, then the final expression becomes like this: del u del x I j is equal to u I plus 1 j minus u I j by delta x plus the truncation error. So, this is the forward difference scheme which is first order accurate, and then we can move to the backward difference technique. So, it is quite similar with the forward difference technique, only we are trying to find the value of the primary variable at a node or grid point which is located at the left side, towards the negative x side of the point P. So, which are so there the value is u I minus 1 j. So, you can see from the location of the grid point with respect to the location initially identified, that is the location P. So, from u I j we can estimate the value of u minus 1 j. So, how we can determine that? So, u minus 1 j we can expand it by as u I j plus del u del x I j minus delta x plus, because why minus delta x? Because here as I told you that it is in the negative x direction. So, that is why we are putting the minus sign over here to show the distance between the point of this I minus 1 j from I j, and then that these are the higher order terms. So, then we are if we simplify it further, so then we are getting u I j minus del u del x delta x plus del square u del x square delta x square by 2. So, and here again we can solve for del u del x I j in case of backward difference scheme. So, we can get some from this equation itself, you can get it. So, I can show that. So, here you are getting basically u I minus 1 j is equal to u I j minus del u del x ij delta x. So, if you want to determine the value of del u del x ij, then you have to, so u I j minus u I minus 1 j divided by delta x, and then the rest are the truncation errors. So, this is first order accurate, again similar like the previous case in case of forward difference. So, now to enhance the accuracy of the technique, accuracy of the solution, we can go for central differencing scheme of finite difference method, which is a second order accurate. So, how do we do that? So, in this case, you can see over here that we can estimate the value, at here you can see the grid point where we need to estimate the value of the primary variable. So, we are considering the values at two different locations which are diametrically opposite to each other at I plus 1 j node and also at I minus 1 j node. So, then so we can construct a finite different quotient of second order accuracy here by simply subtracting previous two derived equations. So, what are the previous two derived equations? So, here we can get the value of the first derivative, that is del u del x I j, which is first second order accurate by so like we have already derived, you can see over here that the expression for u I plus 1 j, this is here, and then we also derive the expression for u I minus 1 j, this is here. So, then if we just subtract u I plus 1 j minus u I minus 1 j, then you arrive at this expression over here, and from here you can quite easily you can estimate the value of del u del x I j, that is the first derivative of u in terms of x. So, for which becomes u I plus 1 j minus u I minus 1 j by 2 delta x, and then these are the truncation error. So, here it is second order accurate. So, in terms of accuracy it is better than the forward as well as backward differencing technique. So, likewise we can also identify the estimate the value for the second derivative, that is del 2 u del x 2. So, how we can do that? Again we, as we told earlier, this is the expression for your ease, it is written again over here. So, the expression for u I plus 1 j that we have discussed before, and the expression for u I minus 1 j. So, now like in case of the first derivative, we basically deducted u I minus 1 j from u I plus 1 j to achieve the value of the first derivative. Now, we are basically doing the addition of u I plus 1 j plus u I minus 1 j. So, you can see the resultant expression which comes from the both the above two equations is like this. So, here you can see. So, then from here you can easily understand that we can just take that E2 u I j to the left side. So, then the expression becomes u I plus 1 j plus u I minus 1 j minus 2 I j, and then divided by delta x square. So, and then the rest are truncation error. So, again it is second order accurate. So, the finite, now we are discussed the simple examples of finite difference scheme. So, now we will move to the finite volume method. So, as I told you earlier that finite volume method deals with the control volume. So, basically we discretize the domain in the form of a number of control volumes, and then the conservation laws are applied to each control volume. So, at the center of each control volume there is a computational node where the variable values are calculated. So, interpolation is used based on the nodal values at the control volume center to estimate variable values at the surface of the CV. So, finite volume can be implemented to any kind of grid, but again it is easier in case of structured grid. However, because of its simplification and ability to adapt to any kind of geometry, flow geometry, so that is why it is often very much popular with the fluid flow problems, where the fluid domain is often changing based on the somewhere the flow is having thicker cross section, somewhere there is thinner cross section, which is not otherwise the case in case of the solid mechanics problems. So, often we use finite volume technique to tackle fluid mechanics problems with relative ease than any other technique, with reasonable accuracy. So that is why, so this is here from the essence of finite volume comes into play. So by design, this method ensures the conservation of quantities provided that surface integrals representing convective and diffusive fluxes are consistent across the shared boundaries of adjacent control volumes. So, one of the key advantages of finite volume is its simplicity in terms of understanding and programming. So, each term approximated in the equations correspond to a physical concept, and that is why it is a favored technique. So, however, it has a drawback when compared to finite difference methods. So, developing higher order accuracy beyond second order in 3D is challenging in case of finite volume method. So, this difficulty arises because the FV method involves 3 level of approximation, that is interpolation, differentiation and integration. So, so for your ease of understanding, these are the two examples, two classic examples of application of finite volume method to simulate the solidification transport phenomena in case of a solidifying billet. And then this is the problem which is shown again before, shown again for your ease of understanding, that is the solidification transport phenomena in case of single track build of a additive manufactured sample, which is in this case it was considered as titanium alloy powder. So, now we will move into the nuances of the finite volume technique. So, this is a typical diffusion equation, it is shown in front of you. So, you can see, so here tau is the diffusion coefficient and phi is any property which can be replaced based on the the problem in hand. It can be temperature, it can be velocity, and it can be other parameters as well, and here S is the source term. So, here a typical control volume is drawn in front of you. So, here this is the control volume boundary that you are seeing over here, and so you can see here that so this is how the control volume length. So, and these are the basically the east and the west nodes which are present at the proximity of this control volume, and basically the center of the node center node of the control volume, that is P, which is situated at a distance between the west and east node at equidistant mode. So, which are designated here as delta x W p and delta x P e. So, this is basically a typical example of a control volume, and then now basically to solve this governing equation that is in front of there here. So, here we basically we need to integrate it. So, we have to integrate. So, this is the typical volume integral of this governing equation. So, you can see this is the volume integral of d dx of tau d phi dx dv plus the source term S dv, again there is a volume integral. So, which can be approximated as tau a d phi dx e minus tau a d phi dx w. That means, it is basically the flux which is going out from the east face of the east node of the control volume, and the flux which is getting in from the west face of the control volume. So, then if you deduct the flux going out minus flux going in, then you can get the net flux. You can also estimate the generation of the flux within the control volume. So, this equation states the diffusive flux of phi leaving the east face minus the diffusive flux of phi entering the west face equal to the generation of phi, and that is, it constitutes a balance equation for the the property which is getting evaluated in this governing equation, a representative property of the flow problem for over the control volume. So, it is the balance equation of that property phi over the designated control volume. So, then so here this is the notes on the interface diffusion coefficient and gradient. So, to derive useful forms of discretized equations in the finite volume method, the interface diffusion coefficient tau and the gradient d phi dx at the east and west faces we need to consider, and the evaluation of property, the property phi and the diffusion coefficient tau needed to be evaluated at nodal points. So, so that is why we can approximate by linear interpolation that del tau w basically that is the location of tau at that the W phase of the control volume, that is over here, and then from here we can estimate. So, it is basically the average between both the phases, that is tau at capital W plus tau capital P divided by 2. Similarly, we can estimate the value of the diffusion coefficient the tau at this east boundary of the control volume, that means over here, which can be designated at tau small e is equal to tau capital E plus tau capital P divided by 2. So, this is by linear interpolation we can arrive at these values of the diffusion coefficient at two phases of the control volume, and then we can go ahead with the gradient calculation at control volume phases. So, the gradients and hence fluxes at control volume phases are calculated using approximate distributions of properties between nodal points. So, linear approximations are the simplest and most common technique for calculating these interface values and gradients, and the central differencing, the approach used for calculating gradients is referred here as central differencing, where properties are linearly interpolated between grid points. And here we have assumed a uniform grid. So, linearly interpolated values for tau E and tau W, the diffusion coefficients at east and west phases of the control volume, are determined based on the nodal values, that is nearest node is the designated as E and designated as P of the control volume, I mean east phase and the west phase. So, this is how we evaluate the values by interpolation, which is shown over here. So, you can see, I mean so the I mean like from this governing equation we are this approximation we are getting. So, if I write the same over here, so you can see the I mean so it is basically the integration of d dx tau d phi dx dv. So, if we can I mean approximate it by I mean tau e a e by delta x, that is I mean between E and P, that is the east phases, and I mean the nodal point P, and then we can approximate is as phi E minus phi P, and then again we can do the. So, here there will be a minus sign, then tau W A W delta x, that is between the west phase and the nodal point, and then it should be because phi p, because phi p as we have seen in the control volume. So, phi p is at the east. So, that is why it should be phi p minus phi w. So, this is how, and we can get the approximate solution for the I mean this part of the I mean governing equation, and then you can see over here it is written like this, and then the integral of the source term over the control volume can be written as the average value that is S bar, and then into d delta V, which is equal to 0, and then from here as we have shown over here. So, from here we can get the expression simplified like this. So, tau E A E phi E minus phi P by delta x P E minus tau W A W phi P minus phi W by delta x W P. So, S bar delta V can be written as S U plus S W S phi P is equal to 0. So, which can be again rearranged like this. So, you can see from this equation it can be rearranged. So, I mean how it can be rearranged, if we can I mean take the all the terms in common for phi p, then we can get tau E A E by sigma x P E delta x P E plus tau W A W by delta x W P minus S phi P is equal to tau W A W delta x W P into phi W plus tau E A E, that is the value of the diffusion coefficient in the east phase of the control volume, by delta x P E, that is distance between the I mean point of interest to the east of the I mean east node of the I mean control volume center into phi E plus S U. So, here you can I mean we can write it this one as the coefficient of phi p at location p, grid point p as a p, and then this point as a w, that is the coefficient of the property phi at west node of the control, at the domain, which is at the west side of the control volume, and this is the coefficient of the property phi at east node, which is situated as the east of the center point of the control volume, that is p, as AE. So, then we arrive at the expression is AP is equal to AW plus AE plus SU. Okay. So, yeah, so here you can understand from here. So, it like we have arriving from here, like we have designated this as AP, this is AW, this is AE. So, then we can get AP phi p is equal to AW phi W plus AE phi E plus SU. Okay. So, here we can identify the coefficients of phi W and phi E in previous equation as AW and AE. So, that these are the coefficients I already discussed, and here you can get the values because we have identified as this is AW and this is AE. So, this is what is written over here, AW and AE, and then because we know that AP is equal to the summation of this minus S phi. So, and then you can see that this term is same as AW, and this this term is same as AE, and this term is same as AW. So, that is why we can quite effectively write AW plus AE minus SP. So, this is how we can identify the values of the coefficients, and then we can move on to a typical problem, that is a one dimensional heat transfer equation, which is written over here, that is ddx of k dt dx is equal to 0, and then we need to calculate the steady state temperature distribution in this rod, which is kept over here. So, the thermal diffuse conductivity K equals 1000 watt per meter Kelvin, and so we and the cross sectional area A is 10 into 10 to the power minus 3 meter square. So, we are stopping over here, and we will discuss the solution to this problem in the next class. Yeah, so bye for now.